Uh, okay. Can everyone see it? It's okay?
Nope,
No?
I cannot see. Oh, no, sorry. Okay,
Okay.
perfect. Okay,
Okay.
all right, Zoe. Stage is yours.
Okay. Okay. Hello, everyone. I'm Zourui from Kyoto University, and thanks for the Armin's invitation and Luke's organization. I'm very glad to share my recent progress about free wave in a two-dimensional directional wave field with photon topography change. And first, I want to give a very brief introduction, but most information, I mean, I said, uh, I born in China, and my bachelor and the master I get in China, and then I go to Japan to get my PhD, and then stay Japan to study for wave and water wave related research. And now I'm working DPI for the Disaster Prevention Research Institute in Kyoto University, and we have so many different directions, different group about most of the civil engineering disaster for the maybe uh, I mean the atmosphere group, and we also have some earthquake, tsunami, and the volcano, and also the geohazard, and also hazard economies. And if you have a chance, you will be welcome to invite to visit Kyoto. Kyoto is a very nice city. So anyway, let's start our today's talk. So our talk maybe have four parts. For we start from the introduction. So my research from my when I was a doctor, we start at frequency, or sometimes we say it a Roger wave, extreme wave height. We found when the traditional wave statistic theory is very hard to estimate the very extreme wave height distribution, especially when the wave height is two times larger than the significant wave height, and we call this extreme wave or freak wave. And one of its generation mechanism we found is modulational instability, and from the Jensen, and we found actually we can call it no resonant four wave interactions if we write the wave energy in terms of the wave stiffness in Hamiltonian form, and we found that the first order terms actually it looks a very small term, but this term is very important in the extreme wave height distribution. And based on this wave theory, we can write a final amplitude in this form. We can call it the Zakharov equation. And from Zakharov equation, we can also write the wave amplitude in the form of we call it nonlinear Schrödinger equation. It's very similar because it has very similar forms in a quantum theory. And now I want to briefly introduce how we estimate the probability distribution of the extreme wave height. Uh, for example, if there is a irregular wave chain, and that is the surface elevation, and there's very two important index. The first is a four wave interaction and three wave interactions, the kurtosis and screwness. This is the force and three moment of the statistical parameter of the wave surface. And this term we can represent the third nonlinear interactions. And this term is the second order interaction in the wave chain. And based on this theory, we can directly give the theoretical wave height distribution, including the uh, modulational instability. And we have based on this theory, we have published a 1D result in the co-engineering and 2D result in the GFM, and then we want to share more details about this model, about its governing equation and the numerical process. So for modified nonlinear Schrödinger equation in a 2D, first we list its nonlinear boundary condition from the Laplace equation and the surface and its energy and the bottom condition, and that they are all no linear forms, at least to the second order. And then we have a mathematical process. First, because no linear term is so many, very difficult. So we need to make the bottom change very mild, and we need to make some method to simplify. So we suppose the bottom change very mild, and we make it explicit, and then we make a multiple expansion method. We divide it into different orders and different harmonics, and then we solve this equation order by order, and diff harmonics by different harmonics, and finally we can give a final expression about this wave amplitude. What we do a little different is we make the bottom depth change a little mild, and it's not a constant deep water. It's from a deep water to shallow water. We can consider the change in the bottom. And if you are curious about more details of this method, that is a different expression at the different orders and different harmonic. Last conference, I heard the professor Philip Liu, his new research about, he expanded this Zourui equation until fifth order, and the terms is full of maybe 2 A4 paper. And I asked him, is there any difference for the final result if we consider fifth order or not? And he said, of course not. So that is just a theoretical discussion. So for engineering, or if we consider the final result, maybe the third order is enough. And from the equation of amplitude, finally we can give a numerical process to construct the surface elevation again. So in this form, and we also have some expansion to consider. First, this can be a small oblique angle here. So we can consider a oblique case when the wave direction has a little angle with a bottom change. Then we can have a refraction process, and we can also, in a very, very special case, we can also consider 2 globes of the oblique wave and their crossing case in a very, very special case. And then I want to talk about how we numerically solve it. Most of the mathematical process you can find in the 40 years paper. You may ask why we still use the result from the paper 40 years ago, because at that time, actually, we don't have so many powerful computer. So we can just give some specific solution. And today we have so many strong GPU, and so we can numerically directly solve this equation and get the numerical result. And if we have some different initial phase and different for example, the Monte Carlo simulation, we can finally to compare their different contributions and to see the difference. And that is the first from a very simple case for 1D. We didn't consider the variety in the y direction, so that is the initial condition for 1D's case, and that is the information about this structure, and it is different structures bandwise, and it's the different bandwise give a different initial surface, and that is we suppose it's initially is in the Gaussian spectrum, because that is very, in this form, it's very easy to control its spectral bandwise. And then that is how we solve it from the beginning. And a little different from a traditional method is we use a FFT method for Fourier transform. And usually we solve it in time and give give the result time by time step. But in our result, we want to show the difference, how the contribution of the bathymetry. So we from the beginning and solve the surface elevation by step by the spatial step from the 0, and as for example from a deep water to a shallow water, we solve it to give a result step by step in this form, and that is 1D's result, and here is the space, and there is the time, and that is the surface elevation, and this is the 2D's case. In 2D's case, we can consider there is directional dispersion for irregular wave group. And in 2D Gaussian shape, now the initial spectrum we have 2 dimensions. First, wave number in the y direction, and that's the frequency spectrum. And so it's in the 2D Gaussian strip spectrum. And we can also consider oblique case. When the wave has an oblique angle, then there is a shift. There's a shift from the spectrum on the y. And in the initial condition spectrum, to make it irregular, we actually add the random phase term in here. And also the same with 1D case. Oh, there's the I, sorry. and that is 2D's result. And because we consider a very large area, so maybe the surface and its direction spectrum is not very significant here. And that is how the wave has this oblique direction, the incident straight wave, and it has oblique for 0.1 and 0.3. And from the different this crest line, we can see how it has a different directional dispersion. This 2 figure is the dispersion is 0.3, and we can see there is almost some part of the directional dispersion. And when the sigma theta is equals to 0.5, we can see the crest line because more dispersion, because there's more dispersion part for different direction. And to finally summarize this result to see its contribution, we make a Monte Carlo simulation because we have a random wave phase in the first. So with if they start as the same initial condition and the same boundary condition for the bottom, and there's only difference is random wave phase at the beginning, then after maybe 50, 2050, and until 2000, the result in this propagation process, it will be the average value will be very more and more uniform, and we can see the final result. Yeah, and this is 1D result, and this is 2D, and this result in 2D and in 1D. And there's an all result about the kudosis mu4, and then we just directly see this the result. First is 1D result, and different BFI means different spectral bandwidth, and we tried 3 different bottom topography with a different slope, a very steep slope and to a very mild slope. And mu4 we can understand it directly about nonlinear high order nonlinear interaction, and it related to the surface distribution and the probability of the freak wave, but we cannot directly equal there. It's only understand as a nonlinear interaction. We can see in a different initial condition, the spectral bandwidth, they give a very different result when the initial very this is a very narrow case, from a narrow case to when the spectral bandwidth from border and border, and there's almost no effect. In a very narrow case, we can see the from a deep water to the shallow water, the mu4 keeps decrease, but the mu3, the second order effect becomes suddenly in the shallow water becomes very large, and especially when the bottom on the slope decrease and back to the slope, the flat bottom. In here, there's this corner and has a very strong after effect, and that is a very similar. We can see a very similar phenomenon in their physical experiment. That is a physical experiment of one of my colleagues, and they did in a wave tank, and we compare our result. Actually, this result is a little different with me because the slope is much more higher to exceed the limitation of the Zourui, but we still get a very similar result, especially in the here. And then that is a directly result about wave height distribution. The green line is the Rayleigh distribution for the linear theory, and the different color from black and blue and red. That is a different result from different slope. And we can see in the black slope, it will give a much more high value when the very large value of the extreme wave height, and that is the 1D result. And then it is 2D. In the 2D, we can see I set different sections from deep water to shallow water, and that is the kudosis in a 2D form, and we can see the kudosis from here. Actually, deep water is there are so many high value, and in this area from deep water to the shallow water, this value becomes lower, smaller and smaller, and in this area, it becomes a rebound process. It become larger again, and after this process, in the flat bottom case, it generally become smaller again, and from a different directional effect, we can also consider it has spectral bandwidth in another dimension about directional concentration. When the sigma theta is very small, it means the concentration is very significant. And then when the bandwidth becomes larger and larger, and we can see the difference from the blue to the red to the yellow. I mean, in the deep water, the very narrow initial spectral bandwidth give a larger value of the kudosis. It means the probability of the frequency is very high, and that is also the comparison of the different slope and the bottom case, and that is a result of the skewness. It means the second order. In second order, we can see almost no difference, because in second order, maybe not depends on this initial condition and its spectral. The spectral bandwidth maybe only from our result. It's only effects on the third order. Third order and relate to the spectral bandwidth. It means the model also means the modulated effect, and the second order effect only depends on the bottom, only the bottom effect. That is very similar to our common sense about wave theory. And then that is QP. QP is we can consider it's a directional spectral bandwidth, and we make it no dimensionless number about spectral bandwidth. We can see the QP also from a different initial condition and the bathymetry, and the bandwidth in the from deep water to shallow water actually didn't change a lot, a little decrease, but didn't change very much, and that is maximum wave height and the maximum crest in our theory. The green line is Rayleigh distribution, and we also consider compare with the second order theory's result, and this line is from a different initial condition and slope, and we can see in the deep water, because the slope effect is very small, so the initial condition, the spectral bandwidth is very, very important. But in the shallow water, the bottom effect becomes larger and larger, and becomes a main impact factor, and that is a distribution of the maximum wave height in a different section from a deep water to generally to shallow water. And we can see the difference, and the conclusion is the same with mu4. Yeah, and then if we estimate the probability of the frequency, if we think this maximum wave height over than the 8 times of the RMS value, because from the Gold's theory, the significant wave height is almost equals to the 4 times of the RMS. So if we consider a frequency, the definition is 2 times of the significant wave height, it means the maximum wave height over the 8 times of the RMS. We can call it a frequency, and we statistic the all of the values in our Monte Carlo simulation. to statistic the ratio of the currents of the frequency, and we directly give the result. Because the model cloud size we use here is only 300, we only want to see their difference. So the result is still not very uniform. Yeah, it has some fluctuation here, but we can enough for us to see the difference. That is the same with what I said before, because in the deep water, at the pH is very high, the initial condition is very important. But in the very shallow water, in this area, the slope angle, the bottom change is very important. And that is for the maximum wave height, and that is a crest. Yeah, that's actually the same. And but crest result of crest gives more result because the second order effect is more important in the crest. And then I also want to see some extension work after the result till now. The first is now we are doing what we are doing. So we want to consider some crossing wave height, even in a very special case. For example, that is a group of wave which oblique angle, maybe the tangent theta 0 is 0.1 in this direction, and this is surface with a different direction. Now we set it to the totally inverse of the minus 0.1, the intersecond, and these two of the growths of the wave chain with different direction, and they start from the same initial condition, and they have the cross. And in a very special case, our numerical model can consider its final combination and the final surface in this area in this form, and we want to see what will happen and what is contribution in this area. The first we just compare the oblique incident wave. So very interesting that because our model has some restriction, we can only consider a small oblique angle. So that is the result of the 5 groups of the oblique wave with a different angle, and we use 1000 simple size to Monte Carlo simulation, and they are almost the same. And I just make it this area and this area very large to tell you they are really from a different 5 groups, but their difference are very small. So I think their difference only comes from the Monte Carlo simulations fluctuation. So if the size is large enough, they will be totally the same line. So our first conclusion is for the very small oblique wave angle, smaller than 0.1, the oblique angle and the refraction in the irregular modulated wave evolution is small, can be neglected. That is the first conclusion. And then we are very curious if it is no contribution about the oblique angle. So that is a result from the two system. In the two system, that is our final equation. And we can see the single system equation from same initial condition. And with crossing case, there is a very difference from a crossing case and the single case. But the crossing case, the oblique angle, because the angle is very small, so their different angle actually no contribution there from the Kudos coolness and also maximum wave height. And then I keep compare their statistical parameter, and I found for the SCD the standard deviation here from a different sigma theta. Actually, they have a difference when the sigma theta become larger and the SCD has is changing, become smaller. So the conclusion now is when the oblique angle has actually have a difference, has a contribution to make the extreme case has a change, but that is too small actually. So in most of cases it can be neglected. And another extension is one of the application. So our model now is we are concentrating on the maybe 200 meters to 1 kilometers. This area and its frequency occurrence of frequency. Now we want to apply to this model to a global model. So what we need is spectral information and wave information. For example, the stimulus, the spectral bandwidth, and some initial wave phase and initial acceleration, and also the initial amplitude. That is all the W3 model can provide it. And also we need target areas bottom informations. And with this information, we can give our correction of the wave height distribution and back to the W3. And because wave 3 extreme wave height estimation only from a traditional way to a second order's contribution, and they didn't consider the third order and the modulated wave train. And that is the work we are doing. So that is part of the calculation result is from the spectral bandwidth without wind around Japan, and we can see it's from almost from 0.3 to 0.6, and in the coastal area, maybe the variety is very large, and with a very large size of the Monte Carlo simulation, we can give a very accurate estimation from deep water to the shallow water about the frequency probability. And that is a different group with different spectral bandwidth. And we can see now the sample size is 1,000. Maybe after we increase to the 2,000 and 3,000, we can give a very uniform straight line. And that is the result from deep water to shallow water. So finally, we can give a table about frequency probability with different input index, depth information, and slope, and spectral bandwidth, and we can directly give the new estimation correction about the frequency, and back to the W3 to make a correction. That is our future work, and that's it, all my talk today. Thank you.
Yep. Thank you very much, Zourui. Very interesting indeed. So we have, as always, 5 minutes for some questions. So please raise your hand if you have a question. So if that's the case, let me just start asking about the spreading angle and the slope, right? So you mentioned that the slope, the bathymetry slope, should be mild, and the directional spread is mild. So we know that weakly nonlinear theory works much better than the physical limitations which is imposed to it. So what is your feeling here, or if you compare with lab experiments which have been done in the past? So what is this? So how far can we go with the slope, and what is the limit basically for the directional spread beyond the physical limitations? But what is small? I would like to quantify. I would like to hear from you how you quantify small, and how much you can stretch the model.
Okay. Actually, the theoretical model of our numerical model, we have so many limitations. We cannot consider a very small directional dispersion. Maybe at least the directional dispersion should be over 0.25, 0.25. I think that's its limitation. If the directional dispersion is smaller than this value, the result cannot be convergent. And after the directional effect over maybe 0.7, the result almost no change, actually, because directional effect after 0.7, they are small enough, so the dispersion is very strong. So I can have compared the result from the 0.7, 0.8, 0.9. Actually, their result no difference. And for the slope angle, actually there's a little another limitation, because in our theory, actually 0.05, I think it's a limitation. We can't make it larger. But most of time in the real world, actually, there's always maybe 0.3 and a very big change. And the current mode maybe cannot consider very cannot very correctly consider this contribution.
Right.
Yeah.
And if you basically model your waves and you fix your wave number, wave frequency, so we know
Yeah,
that when the waves propagate over a slope, you have wavelengths becoming shorter or wave numbers becoming larger.
yeah.
So how do you deal with that in your framework?
I mainly the wave number and we make the wave stiffness is constant.
Right.
Yeah,
So you don't
yeah,
consider
and
basically the shoaling effect, right? So
yeah.
okay, I see. Yeah.
Thank you.
Okay. So let's see. So yeah. So we are actually a bit way over time. So maybe it's better to hand over to Marie now.
Mhm.
And yeah. So
Hi,
Marie
hi
will take it from
everyone.
here.